Hello, and welcome to another session at GenNation 2020. My name is Leon, and I will be hosting the session for you. Thank you for following us today, and also a big thanks to our sponsors for making this event possible, especially in these times. And finally, a big thanks also to the two people who are here for you to see and hear, and that's Kyra Wulffert and Andrea Frittoli. Hi, Kyra. Hi, Andrea. You're joining us from Cardiff, right?
Yes.
Yes.
Perfect. How are you guys doing?
Great. Yes. Excited to be here.
Great. It's also exciting for us to have you here. So they will be doing their talk about machine learning for continuous integration, which I'm also quite curious about this topic as well. But just right before we start, just a reminder that you can ask your question on our YouTube channel or also on our Slack channel, and feel free to also react to any comments on or comment on any of the questions. Andrea, Kyra, the floor is yours. Good luck.
Thank you.
Thank you. Thank you, Leon, for the introduction, and thanks everyone for joining our call here today. Well, we introduced us already, but my name is Andrea Frittoli.
And my name is Kyra Wulffert.
Yes, and today we are going to talk about how we applied machine learning to continuous integration. A couple of words about the team. So Matthew and myself, we used to maintain a rather large CI system. And so we worked daily on making sure that the CI system was running smoothly, and we had to triage failures and understand what was going on. A lot of failures, well, not so many failures, but it was a large CI system, so it was more than a small engineering team could handle easily. So we had the idea that maybe AI or specifically machine learning could help us here in dealing with this problem. We did have the domain knowledge for the CI type of environment, but we kind of lacked the expertise in the machine learning area. So we asked Kyra whether she wanted to join us, and luckily for us, she joined the team. And so we were able to kick off this project. And we had our machine learning expert on board. Before I dive in, I just wanted to say a couple of words on continuous integration. So nowadays, continuous integration is a good practice, standard good practice for software development, and even more so in open source projects. So continuous integrations has many definitions, but basically it means to continuously test the different components of a software together every time a change is made to the software, or even every time a change is proposed to the software. And if your open source project is successful, you have a lot of contributions. And a lot of contributions then imply a lot of testing, a lot of CI jobs being executed. A CI job is made of several tests which are executed to verify that things are fine in the change that has been proposed. And if you look at the numbers for the open source project we're working on, this is on the ordinate. It's actually tens of millions of tests executed daily. So even though things were normally running smoothly, from these numbers you can imagine every now and then failures happened. And all this testing produced a lot of data and a lot of logs. And the beauty of this is that because it's open source, also the data produced by the testing is open source, so it's open data. And we thought this is actually a great opportunity for us to jump in and do some machine learning in the open. The specific project we were working on is OpenStack. OpenStack is a cloud management tool. So it's a set of APIs that allows you to manage virtual resources of different kinds, like virtual machines, disk, networks, and even other higher level abstractions. Integration testing for OpenStack means in a virtual machine as a test environment, actually deploying a cloud within the virtual machine, and on this cloud creating nested virtual machines, disks, and networks. All these resources generate a number of different resource utilization on the virtual machine that is being tested. So you can see on the right side, there is the graph moving, show different examples of normalized system average load from virtual machines that were executing tests. So in OpenStack, every time a change is proposed to the system, we run integration tests on it, which means that the software is verified that all the tests are passing. The code is also reviewed by a human being, and once the code is approved, the change is tested again through what we call gate testing. So in gate testing, we already know that the test passed and the code is good quality because it has been reviewed, but we test it again nonetheless before merging to making sure that perhaps rebasing the code, nothing went wrong. And so we saw some failures, more failures than we expected in gate. And we often suspected that these failures might be related to load on the virtual machines, our test environments. So we started collecting data from the test environments. Because the test environments are ephemeral, during the test, we write logs, system logs, application log, and we started using a tool called dataset to write a log that contains key metrics on the operating system, like disk I/O, CPU, network utilization, and so forth. So before the test is, when the test is completed, before the test environment is destroyed, these logs are taken out of the VM and uploaded into an external storage. So we thought we had this distance data, and we thought this would be the ideal point for us to start working with machine learning, because this data is numerical data. So it's in a shape that is already almost suitable for applying to a machine learning model. And we wanted to verify if load was creating us issues. Also, something that we considered is that this data is not OpenStack specific. So the same methodology that we were going to work on could possibly be applied to other different systems in the future by collecting the same type of data. Because of the amount of changes that happen in the CI system and the amount of logs that are generated, it is not possible for the OpenStack community to store so many CI logs over time, so they are rotated quickly. And we soon realized that the amount of logs available on the log server at any point in time was quite not enough for us to run a good training of our machine learning model. So we started collecting logs and storing in our own storage. The way we did it, we wrote a function, which is part of what we call the CML project. So CI, machine learning for CI, CI/ML, which we call CML. And what this function does, we containerize this function and we run it as a periodic action in OpenWhisk, which is a serverless platform. And what this function does, it collects the new logs from the OpenStack CI log servers. It performs an initial validation just to make sure we're not storing data that is not valid. And then it stores the raw data in a object storage in the cloud, so cloud bucket. So that was the raw data stored in a bucket. So even though the data is numeric, there is still some preparation that we had to do. So first of all, we wanted to visualize the data. So we started looking at the data, visualizing the different metrics from the system. So how the graph for the disk I/O or the network I/O or the memory or CPU utilization looked like. Several of these graphs already could be said to be heavily correlated, so they have similar shapes. So we didn't want to use all of them to train our models, because it would just be extra data that provides no value. So we wanted to be able to select and filter the data. For that, because the experiment with the caching worked quite well, so we took a similar approach. We wrote a new CML function, which takes the raw data from the bucket in the cloud, applies filtering and normalization, and stores the resulting data pre-normalized, ready to be fed into the training, into a different bucket in the cloud, so into different object storage. So one thing that was important when defining this function that we realized is that we needed the function to behave in a consistent way and reproducible. It's very important for us that the creation of our data sets was reproducible, so that if we had to recreate the data sets, we could then run the experiment and then have the same results again. Just to give a better understanding of what's going on, here is an example of what the DIStat data looks like. So this is a very small table on the right side. So the DIStat data, in fact, will be much larger, but you can get an idea of what is going on from here. So the columns are the different features or the different metrics from the operating system. USR stands for the user CPU utilization. Used refers to memory, and then you have disk I/O. 1M is the system average load, average over a minute. It's a metric that is exposed by Linux operating systems. And so there are 20 or more of these columns. And rows are samples at different time intervals. So you may be able to read there that we are collecting data every second. But we thought that this was too much resolution. It would be too computationally heavy. So we decided to downsample our data to different time intervals. In creating the dataset, there's something else that we had to care for, which is general data cleanup. One may imagine that data is perfect and always clean and as you expect it to be, but in fact, you often find that for some reason, a metric could not be recorded at a certain point in time. So you find holes in the data, so you have to be careful and catch things like not a number and so, which might break your training. So if you look at the crossing of the lines with the columns here, you see there are 6 numbers that we are taking in this specific case. And what we did for these 6 numbers, we unrolled them into a vector, a one-dimensional vector. So on the left side, you see now 3 vectors, starting from USR1 to 1M3. Each of these vectors with 6 numbers represent one CI job that was executed. In fact, this is just an example to make it fit on the slides in reality, because CI jobs run for more than 1 hour. Even with a downsampling to 1 minute or so, we usually had a number of features between maybe 150 and 200. And the final step we did was for normalization after the unrolling is the normalization. So you can see on the left side numbers have different values depending on the metric that has been recorded. We wanted all of our numbers to be between -1 and +1. So we applied a standard normalization function there. This just makes computation much less heavy. So it makes it easier to run faster. So to summarize, for a function to build a data set, that filtering normalization, but it also split our data in 3 groups. So training, dev, and test. The training we use for training our models, the test we use for the evaluation phase, and the dev for the fine-tuning. The data set, once it's produced and normalized, also stored on object storage. We use the S3 protocol, but it can be on any cloud. We also defined input functions for training and evaluation. So the input functions takes the data from the data set and it splits it into batches and epochs for the model to training to consume. So we had the data here, but we wanted to bring this data into actually training the models. So the next steps that we had to do was define the hyperparameter for our experiments and then actually run the training. So again, we followed the same type of approach. We wrote 2 functions. the CML setup experiment and the CML train model, which respectively are responsible for defining an experiment and running the training. All these functions have the great advantage that can be easily executed, dockerized or containerized, executed in a container, which means that because they're also able to work with object storage, they're easy to run in the cloud, which is particularly important for things like caching the data that we want to do on a regular basis, but also for running the training, which is still computationally heavy, and we want to run many of them. So we want to be able to distribute those trainings into different kind of infrastructure. So talking about the training infrastructure, we wrote this wrapper, as I was mentioning, in CML. The wrapper, one of the reason of having this wrapper, apart from easiness of containerizing it and running it, was that we wanted to be able to interchange the machine learning framework behind the scenes. So we wanted to have like a single interface for running a training that behind the scene could work with TensorFlow estimators API, which we did most cases, but we also used things like Kyra or scikit-learn for different type of training. So we wanted to have a common interface for that. In terms of training infrastructure, initially we run our trainings on our local laptops and machines using local storage, the disk. It is possible to run CML from a Jupyter notebook that we did in many cases as well. And then once we were ready to start, we had many data sets and many experiments defined, and we wanted to run all of them across many days. We started using a tool called Fiddle, which works on top of Kubernetes and helps you schedule jobs, which are training of models on top of Kubernetes cluster. After a while, we switched back to a different approach because we wanted to have the minimum possible footprint in terms of training infrastructure. So we wanted to focus the utilization of our resources on the training itself and not consume cloud resources in complex tasks of scheduling or tracking metadata. So we wrote a few tasks and pipelines in Tecton, which is a cloud-native pipeline controller, which allows you to define tasks and pipelines to be executed on top of Kubernetes. So with these tasks and pipelines, we could run our trainings on top of Kubernetes cluster. So initially, we provisioned a few bare metal nodes, and we provisioned our Kubernetes cluster on top of these bare metal nodes with GPU cards in them. We did a few tests, and we realized that, in fact, GPUs were not bringing a significant difference to the table in terms of performance for running our trainings. This has to do probably with the fact that we are running DNN. So we switched back to provisioning our Kubernetes clusters on top of regular VMs, basically. Yeah. So there are other systems that would do similar jobs, like Kubeflow pipelines. But again, we wanted to keep the footprint as small as possible for a type of project. We didn't need a large system. So finally, in terms of predictions, so once we had our trained models, how to make predictions from the model, we wrote a simple Flask-based API that exposes prediction for every synchronous response from the trained model and a Helm chart to deploy that. But also we wanted to support a more asynchronous type of workflow because it turns out that the OpenStack CI system is able to generate events every time a CI job is complete or it starts. But interesting for us when it was completed. So through a system called OpenStack Firehose, using a protocol called MQTT, a client may subscribe to events and be notified every time a CI job is complete. So our MQTT client listens for such events And whenever the job is complete, it goes onto the log server, downloads the new data, the dataset data, applies the normalization functions on the fly, so it creates, it normalizes the data from it, and then it runs a prediction. So the prediction can be generated this way, can be used to provide more context to the developer who made the change to OpenStack, or to the engineer that is going to triage an eventual failure in the CI system, because it can provide more context or information coming from the prediction that was done from the training. The way this could be implemented, for instance, is to push back a comment onto Garrett on GitHub saying what was the result of the prediction. So yeah. One last thing that we thought it might be possible to do is what we call continuous training, because we consider the CI system as a trusted source of data. So we can take new data from the OpenStack CI system and use it to continuously train the model and decide when we want to switch to new model trained with more data. So next for the experiment.
So hello, everyone. So with the workflow and the infrastructure in place, as Andrea explained, we plan for a series of experiments to find insights using machine learning on this available distant data. The first set of experiments we ran were supervised learning on binary classification. Our aim here was to train a model that could predict accurately if whether a CI job was passed or failed. So for this, we use a classic deep neural network classifier, and our dataset was based on one specific CI job called TensorFlow, which is a CI job that is quite popular in the OpenStack integration. And as Andrea explained before, we were using data coming from the gate pipeline only because this data was less noisy. As hyperparameters for our model, we were using a ReLU activation function, sigmoid as an output layer function, which is quite handy for classification problems. We went for the AdaGrad optimizer, which is self-adapting. We started with an initial learning rate of 0.05, and as we can see in the figure, our network topology contained 5 hidden layers, and in each layer we had 100 units. So our primary metric was accuracy. We were also having a look at the loss. And first of all, we wanted to evaluate if there was one feature or a combination of features that could provide the best accuracy for this binary classification problem. And so in our original data set, we had user CPU, use memory, and average system load as features. And we started with a data resolution of 1 minute, and found that, as we can see in the figure up above, there we are displaying 1 minus accuracy for visualization purposes. We can see there that the best accuracy was achieved for the feature combination of user CPU and system load. And we got a pretty high accuracy value. Nonetheless, we wanted to see if a better value could be achieved, fine-tuning. So we ran the experiment with this good combination of features, but now changing the data sampling, the data resolution, ranging from 10 seconds to 10 minutes. And it was unsurprisingly, but with the data resolution of 10 seconds, the accuracy was better, but the difference was really tiny. So we had a look at the metrics to see if maybe in the precision recall or the F1 score, which is the weighted average of precision and least recall, we could find some insights if there was a significant difference to justify having the data resolution of 10 seconds. But the values were very similar, so we decided to keep our model with a data resolution of 1 minute because it was less computationally costly. One important point we wanted to evaluate during this set of experiments was whether the trained model, besides predicting if the CI job was pass or fail, was portable. So what we did is we took the trained model and we evaluated with another data set based on a CI job called TensorFlow PI3, which is very similar to the TensorFlow CI job, but it uses Python 3 and it has one less component. And we found that the metrics were pretty good, not as good as the ones obtained with the TensorFlow dataset, but high enough to say that the model is portable to similar CI jobs. So this one was one of the main findings from this first set of experiments. Another important point we found was that with our estimator, the model was providing the prediction, so whether the CI job was fail or pass, but it was also providing a prediction confidence. And this value might be quite useful, especially for CI operators, because if this prediction confidence starts to degrade or degenerate, it could be used as an early warning system to flag that something is overloading or is starting to fail in the system. So this was a very cool finding from this first set of experiments. Our second set of experiments was using supervised learning again, but now on a multiple classification problem, where our classes are the hosting cloud providers, which are the cloud operators providing the virtual machines to run the CI jobs. In our data set, we had initially 10 classes, and we use again TensorFlow as CI job and data coming from the gate pipeline. Initially, we had the model with the same hyperparameters as the model we trained in the previous experiment. And we ran the evaluation and found that the accuracy was not good. So following the same approach we did before, we first tried to find if there was a feature or a combination of features that could provide a better value, but it wasn't the case. So we tried then changing the data resolution, again, ranges from 10 seconds to 10 minutes. And there was a slight improvement, but not significant. So as a third step, we changed the network topology. We tried the test with more complex and less complex network topology, but still no real improvement was achieved. So at this point, we thought there is something in the data that is not good for the classification model to be able to distinguish among classes. So we went back to the data and found that there were some classes that were the same cloud provider, but in different regions. So we decided to reduce those classes to one. So that means one cloud provider in several regions was considered as just one class. And with this reduction, we passed from 10 classes to 6 classes. And then we ran again the process I just described before. And in the first experiment, already the accuracy was significantly better. So that was the trick that helped us start in predicting in a more accurate way. And again, we tried to fine tune, and we found that using a less complex network topology, the accuracy improved. So having a look at the metrics for this trained model, we found that for those cloud providers with more samples in the dataset, the metrics were high and good. And when we ran this experiment, there was a new cloud provider with very little samples in the dataset. And for this, of course, the metrics were very poorly. So this gave us the inspiration to try if a model using unsupervised learning will be able to cluster and group all these cloud providers with a higher support in the dataset, with a higher amount of samples in the dataset. So for running this clustering experiment, we used the basic dataset with the combination of features, user CPU and system average load, and the resolution of 1 minute. As algorithm, we used k-means, which is the most popular clustering algorithm. And our expectation was that it will make sense to have a number of clusters that will be the same as the number of cloud providers with the highest number of samples in the dataset. So they were between 3 or 4. But we wanted to validate these assumptions, so we ran the elbow method, and we also calculated the silhouette coefficients. And the recommendation there was to have between 3 to 4 clusters. So those were the 2 experiments we ran. And we found that for the experiment with 3 clusters, the one cluster was containing 2 of the main cloud providers. So it was not significant for our purposes. But in the experiment with the 4 clusters, each cluster had one of the cloud providers with the higher support in the dataset. And there was one cluster that had very little noise. So over 90% of the samples in that cluster were belonging to the same cloud provider. So that means this cloud provider had some features in the distant data that were quite distinguishable for the model to separate and group them. So in summary, from these multi-class experiments, we found that reducing the amount of classes helped to improve accuracy. Our explanation is that cloud providers tend to use similar hardware layout across regions. So from this point of view, it makes sense to reduce the classes, and it helps us to achieve a better accuracy. And we also try to see if this model was portable to similar CI jobs as we did with the binary classification, but unfortunately the results were not good. We found as we saw that clustering has huge potential in this data, and that higher support helps for better clustering. So in general, at the beginning of the project, we had the suspicion that that many of these failures coming on the gate pipeline were due to system load. And with our experiments, we could verify this suspicion, and we could also predict with good accuracy those failures having only system data. For those failures that are outliers that could not be predicted by our model, it's likely that the cause is not system load related. And knowing this alone is very helpful for engineering to triage failures and further investigate. So we saw also that clustering and unsupervised learning has a potential with this data. And this is important because doing classification of single failures could be a lot of effort from the engineering point of view. And if we have a model that could do a first approach with little effort for the engineers, that could be a good and a huge help for the triage of further investigation of these failures. As a project, so we found that it was really important and crucial to start collecting data since the beginning, especially because we had open data, and it was also crucial to have a cloud infrastructure and a workflow that could allow us to work and contribute from remote. We were all working from different regions and time zones, and it was also very helpful to have infrastructure to train on the cloud. So it was, as we could see during the multi-class experiments, it was important to have knowledge domain, and otherwise we could have not moved forward during those experiments. And we were quite open about using machine learning tools. So we didn't stick to a framework. We were using for some of them TensorFlow, and for the others, scikit-learn and so forth. So as future work, we started exploring the interpretability of our binary and multiple classification models. We saw already that for binary models, there are some time frames where there is huge contribution to the prediction. So this is a topic we want to further explore. Another interesting point to expand will be to extend the dataset and include some more information from the system and application logs, and maybe use NLP to further classify the failures. And as mentioned before, exploring the clustering of failures has a huge potential. And another topic we would like to explore more is the CI job portability, which works for the binary classification model, but not for the multiple classification model. Okay, so this talk and all our code are available in GitHub, in these links. We will also share them in Slack. And we're here open for questions. And if in the future you have questions or you want to contact us, we are available for you. So thank you very much for being here and listening us in this virtual talk. And thank you to J Nation for inviting us.
All right, thank you very much. So maybe just a couple of quick questions before we finish this session. So actually, I have one question that I really like to ask when people talk to me about experiments that they run, especially that they're so extensive. What do you think are the biggest? What were the biggest difficulties that you would say you would have while running the experiments, and what were the biggest blocker that took really a long time to get through?
So the beginning, the data, deciding what was useful in the data, and for me, this topic was quite new, OpenStack and CI integration. So it was crucial to have Andrea and Matthew giving their insights and their knowledge domain. So I think that was the biggest hurdle to overcome at the beginning. And then when we were training, when the results weren't good, that was again the crucial point that helped to move forward, knowing your data.
Yeah, I think that's the biggest thing. It's either there's a lot of data, but then you don't know how to but it's not labeled, or then you don't have enough data. It's usually how it goes. All right. And how do you what do you see the impact of using this approach? So you've talked a lot about the future work and you have, and let's say that you managed to actually accomplish those things in 2-3 years. What impact do you see from this?
Well, the idea was that we would be able to use this approach in production in OpenStack. I mean, since we started working on this, both Matt and myself and Kyra too, we changed jobs, so we are not focusing on OpenStack anymore. But the idea is really like I showed when I showed in the prediction pipeline, to have like near real-time insight from these models. It could be published directly to the developers to give better insight of what is going on. So both as a reviewer or as a developer and as a maintainer of CI system, I've seen people often get frustrated if there is a lot of load on the CI system and your tests are failing, not because you did something wrong in your code, but just because maybe there is too much load in the test node or some transient failure in the CI system. And if you can put there a message saying, look, sorry it failed, but it was not because of your code, so feel free to rerun the test, that would be really helpful. So that's kind of the direction we're trying to go towards.
Oh, that sounds really amazing. I think that could improve the lives of a lot of developers. All right, guys. Well, thank you very much for your time, and thank you for taking your time also to coming up and showing your presentation, sharing your knowledge. I think it was useful for everyone. And yeah, this talk will be available later on also online for anyone who just jumped in the middle. And again, big thank you for anyone who joined, and see you in around 15 minutes. Bye, guys.
Thank you, Leon.
Bye.
Thank you, everyone.